Please welcome Sebastian Cioaba for our afternoon session, who is from University of Delaware and is going to tell us about optimal distortion embeddings of distance regular graphs in Euclidean spaces.
Thank you, Maria. Thank you, everyone, for coming to my talk. I want to thank the organizer, Ada, Tino, and everyone else for inviting me to give a talk. I'm not going to have much quantum in my talk, but there'll be some hopefully interesting algebraic graph theory. So I will talk about optimal distortion embeddings of distance regular graph in Euclidean spaces. So let's start with the with embeddings. So if we're given a graph G with vertex set V and edge set E, an embedding of the graph into some Euclidean space Rm is just an injective function from the vertex set into that space. So it makes sense to make it injective. You don't want to represent two vertices by the same point in the space. So associated with this embedding, so that's just what an embedding is. You have these quantities. So the first one is I denote it by X. That's my notation, but it's usually called expansion of rho. And that's so since everything that we're talking about is going to be finite, it's going to be the maximum over all the vertices X and Y of the ratio between the distance in Rm between the images of these vertices X and Y, and the distance dxy in the graph between the two vertices. And similarly, you can define the contraction of rho, which is the maximum, again, over all the vertices x, y in V. So obviously, you're going to take x not equal to y of the other ratio, between the distance in the graph between x and y, and the distance between their images in this space Rm. So this M could be anything. Could be the line, could be the plane, could be anything. And now, so you have this embedding, which is this injective function from the vertex set of the graph into Rm. And you have these two quantities, expansion of rho and contraction of rho. And you can define the distortion of rho. This is this parameter associated with this function rho and the graph G. And this is going to be just the product between the expansion and the contraction of rho. So it's a measure of how well you can embed this graph into this space. And what I'm giving you here is just from this notion restricted to the graph situation. This is much more general notion that can be defined for metric spaces, finite metric spaces, I think arbitrary metric spaces, and so on. But here I'm just going to talk about graphs, embedding graphs, finite graphs into Euclidean spaces. And now, so for any embedding rho, you have this parameter distortion of rho, and what I call the least or the optimal distortion of G is defined as the minimum of this distortion associated of rho as rho goes over any embedding. So again, rho can be any injective function from V to Rm for any M. Okay. So again, for me, least or optimal distortion will be the same thing, and it's the minimum of this quantity over all possible embeddings of the graph. Okay. Now this is a quantity that's well studied in mathematics, in computer science. I can give you references at the end, so on. So let's do some examples. So let's take the complete graph Kn. Well, if you take any embedding, so again, rho is an injective function from the vertices of Kn into Rm. The distortion of rho is the product between the expansion and the contraction. Now, the expansion measures how far the images of the vertices go from each other. But you know that in the graph, the distance between any x and y is 1. So for the expansion, you just have the maximum over all xy, again, x not equal to y, of the rho x minus rho y. And in the contraction, you have the kind of the maximum of the inverse quantity. And you do a simple calculation and you get that this distortion has to be at least 1 for the complete graph. And you can embed each vertex as its characteristic vector, let's say in Rn, if the graph has n vertices, and you can achieve this distortion. So this gives you a proof that this least distortion or optimal distortion for the complete graph is 1. So that's not too hard. Okay. All right. So here's another example, a bit more maybe difficult. But so let's look at the cubes. So you have the n-dimensional cube Qn. Here you have the vertices are all words of length n over the binary alphabet to 0 and 1, and 2 vertices are adjacent if and only if they differ in exactly 1 position. And in this situation, the vertices, as we all know, can be, they're binary vectors in Rn. So you can embed each vertex as itself as the column vector. And if you do again the calculation of the expansion, well, the distance between the images, like you can do these calculations, and you can actually get that the upper bound is at most yeah, I don't know why I put there rho x much, but you can get that the least distortion is the most square root of n, and this is the actual value, and this is a result that was proved in '69 by Enflo, and then Lineal and Magen gave a proof in 2000, and Valentin, whose work I will talk more about later on, gave a proof which I'll explain, a more general proof for Hamming graphs, for any not just binary Hamming graphs, but QRE Hamming graphs. He determined this least distortion. So I'll talk about that later. Now, so again, the definition of the least distortion is this minimum over all rho of this expansion times contraction. But you have an equivalent formulation, and this is sometimes used, and I'll use it here just so that I lead you to another formulation for C2 of G. The equivalent formulation for C2 of G is the minimum of D, with the property that this function rho satisfies this inequality, that for any xy in any vertices x and y, the distance in the Euclidean space between rho x and rho y is at least the distance in the graph between the vertices x and y, and it's also at most this number d times the distance dxy. So you can go between them. It's not very difficult to show that these two definitions are equivalent. So I will use both of them. Let me see. There's something in the chart. Yeah, because I'm doing so. This is I'm using the L2 norm. There's a 2 here. You can talk about CP, which is using the LP norm, and people study those as well. So here I'm just going to use the L2, just the L2 norm. Thank you for the question. Okay, so with this equivalent formulation, you can get into, again, you can find another equivalent formulation using Gram matrices. So on the top, I just have the last blob from the previous page. C2 is the minimum of D, such that the distance between rho x and rho y is between D of xy and this constant times D of xy. Now, if you take this rho x, they're vectors in this space Rm for whatever m is, and you can take the Gram matrix. So Q of xy is going to be just a rho x dot product rho y. So you can just take the Gram matrix of these vectors, and if you square that those inequalities on the top, you will get that the distance of xy square between x and y square is less than or equal than the distance square between rho x minus rho y square. And when you calculate that, it's just the qxx, it's the middle expression there. I won't read it. And then on the right hand side, obviously, you just get the square of the corresponding right hand side. So now you it's equivalent talking about these vectors rho for each vertex, and talking about this v by v positive semi-definite matrix Q, which is the Gram matrix of these vectors. Okay, so now so this is a result that was obtained. So this is a it's a SDP, semi-definite programming formulation of this listed distortion constant C2 of G, and this is due to linear London and Rabinovich in '95, and here it's C2 of G. The square of C2 of G is the minimum of this. So this constant D that I had before, which appeared here as a kind of like a D square, was replaced by this C. And so now you just have from the previous equation, you can say that C2 of G square equals the minimum C, subject to this constraint that you have this V by V positive semi-definite matrix Q satisfying these inequalities. So again, here the Q's are in the middle here are the entries from the matrix Q, and on the outside you have the parameters which are related to the graph G. That's the distance in the graph between X and Y, and also here the same thing. And you have this constant kind of keeping things between. Okay. Now, so using this, I won't give a proof of it, but you can look in their paper. They gave another formulation for the listed distortion. So they meaning linear London and Rabinovich. And here we use a set of all n by, so again, the graph that I have has n vertices. So we're looking at n by n positive semi-definite matrix Q, whose row sums are 0. So you have this extra condition. And they prove that you have this upper bound on the least distortion, C2 of G is at most D, if and only for any Q in this set, so positive semi-definite with row sum 0, you have this inequality that those two sums, which involve the entries in the matrix that are positive versus the entries that are negative, is less than or equal to 0. And from this relation, they proved this different characterization of C2G, which is the maximum over all matrices Q in this set ON of this strange looking quantity, which is so it's a square root of this fraction, and on the top you have a sum over all the positive entries in the matrix Q, and on the bottom you have a sum over all the negative entries in the matrix Q. Okay, so that's again work done by linear London and Rabinovich in '95. Okay. Now they prove more. So they actually proved that if you have so this is, I just rewrote the previous characterization on the top, and they prove that if you have this an optimal embedding row for the graph, and you have Q a matrix that attains equality in this bound here, okay, Q attains equality, then you will know something about the pairs XY where Q of XY is positive, and you'll know something about the pairs XY where Q of XY is negative. So they prove that QXY is positive. So the terms in this summation correspond only for those pairs XY that are the most contracted. So those pairs XY which attain equality for the contraction of rho. Remember that the contraction of rho was they attain a maximum of the distance of XY. So over there, you're only going to have pairs where that maximize the distance between the graph. Let me put here different A and B divided by the rho of A minus rho of B divided by 2. So that's what comes up in the top. Those are the only terms that are going to be appearing in the top. And then in the bottom, you're only going to have terms for the most expanded pairs rho of xy. So over here, you're only going to have those pairs xy that attain equality in this other, that maximize this ratio, rho of A minus rho of B divided by DAB. Okay, so they're trying essentially yeah, I'm not going to give you the proof here, but you're trying to find this constant. So can you simplify this summation? This sum, and that's kind of the logic here. You can, the numerator involves only the most contracted pairs, and the denominator involves only the most expanding pairs. I mean, of course, you can think that this is a bit of a catch-22 because you're trying to find the C2 of G, but to find a C2 of G, you need to know the row. So it's kind of, which one comes first. Okay. So for all the others Q, you can, the Q is gonna be 0. Now they prove something more for the summation that appears here at the denominator, the most expanded pairs. They show that that's always going to be attained for adjacent vertices. And that's just an application of the triangle inequality, because if you take any pair of two vertices x and y, which are not adjacent, again, I didn't say, but all the graphs are connected. So you take a shortest path from x to y, and you remember that this expansion of rho is the quantity over here, the maximum of this value, and it's easy, on the, if you take this shortest path between x and y, you can apply the triangle inequality, like the first inequality here. You have the triangle inequality in Rm on the top, and at the bottom, these two things are the same because the distance between xi plus 1 and xi is 1, so they're the same thing. But then if you have this this ratio of these two sums, each of them that has k terms, then this ratio is going to be less than or equal than the maximum over all I of the ratio between pairs of adjacent vertices. So if you're trying to maximize this this quantity, you will always have an upper bound here attained at two adjacent vertices, and that's exactly the gist of this proposition, that the expansion is always attained by adjacent vertices. So that again simplifies things. We'll see in a little bit, because here, if you know what happens for the adjacent vertices at the denominator, means that you know what D is going to be 1. So you just have to sum up this Q over all adjacent minus Q xy over all adjacent vertices. But there's no such thing. We'll see that this is a bit of the crux of the matter. There's no such result for the top. Like you cannot quite tell, okay, where is the summation on the top? What can we say? Okay. All right. So let me give you some other results. So there's a result of Bourgain that is highly cited and very important. This is quite general, that every metric space with n points can be embedded into an Euclidean space with distortion big O of log n. And people, again, Lineal, London, and Rabinovich, and Matuszek, independently, they prove that this bound is tight. And this is attained by a graph metric of expander graphs. So they actually, expander graphs attain this upper bound. They give you the largest least distortion. So the following is the easiest proof that I can understand, and it's a proof due to Lineal and Magen. They have a paper in 95 in JCTB, and they prove a concrete, I like it because it deals directly with eigenvalues, and they prove that if you have a k-regular graph, again with n vertices, and you have a spectral gap. So epsilon here, I use their notation, but don't think of epsilon as being small, and think of epsilon as something that does not depend on n. This, you have some non-trivial spectral gap between k and lambda 2. then they prove that there is some positive constant that depends only on k and epsilon, such that the least distortion of the graph is at least this constant time log n. So if you have expanders, as you all know, this epsilon is large. It can be, as large as k minus 2 root k, and you can get this lower bound or log n. Okay, so how in the world would you prove something like this? So what they use the previous formulation that C2 of G is the maximum of that quantity delta of Q. So it's just a matter of coming up with the right Q, right positive semi-definite matrix. And so here's the first step. The graph is k regular, so you can count. You have an obvious upper bound on the number of vertices in a ball of radius r, because it's the number of vertices in a tree, in a k regular tree with that height. And here this is not optimized, but you get this upper bound of roughly k to the r. And then they define a graph with the same vertex set as G. It's kind of like a distance graph, but X and Y are going to be adjacent in this graph H if they are far apart in the graph G. So if the distance between X and Y is at least log n in base K minus a little bit. And now by these definitions, it's not very difficult to show that if you pick the right number here and you do this calculation here, that every vertex is going to have every vertex X, you look at this ball, you look at all the vertices at distance at most log n minus 2, and there are going to be many vertices here that are far apart from it. And actually, they're going to be at least n over 2. That's why these numbers are chosen like this. And what does that mean? That means that this graph is Hamiltonian. Like you have this result of Dirac that if you have at least n vertices and degree at least n over 2, your graph is. But they don't need the Hamiltonian cycle. They want a perfect matching. So let's just do this for n even. So this graph H has a perfect matching with adjacency matrix B. So you basically have these pairs of vertices, X, Y, that are far apart in the graph G, between them. So you paired up these vertices, and then you define the matrix Q. And so it's defined as K times identity minus A plus this epsilon over 2 B minus I. Now, clearly, Ki minus A, that's going to have, if you multiply by the all one vector, you're going to get 0. And B is the adjacency matrix of a perfect matching. So it's a one regular graph. So if you subtract 1 from it, it's also going to do the same thing. So that explains that Q times 1 is 0. And it's not difficult. A has all eigenvalues less than K. And it's actually, well, here you have to do a bit of work. You use the spectral gap to prove that that this matrix is positive semi-definite. It's not quite the sum of two positive, like Ki minus A, it is positive semi-definite, but B minus I is not. Its smallest eigenvalue is minus 2, but you with the spectral gap of epsilon and with the epsilon over 2 from here, everything works out perfectly fine. So that's why it's epsilon over 2. And then you have a matrix that you can plug into that expression from London, Lineal, and Rabinovich, and you get C2 of G is greater or equal than the square root. But now you know exactly what you're summing up at the bottom. You're going to sum up over all xy's that are going to be here. We don't even know the embedding. I know I'm summing up over all xy's that are adjacent. And so you see the only negative entries in Q are over here, are at minus A, and they're the adjacency matrix ones. And if you sum all of them, you're going to get K times N. So that's because the distance is 1 square is 1, and you get that. And on the top, you're going to get this d square of xy times q of xy. But now the Q of xy that are positive here, they're gonna come from this epsilon b, epsilon over 2 times b. So those entries are gonna be epsilon over n. And the distance between x and y that are gonna be positive, they're also gonna come from this b, and the distance between them, the way B was defined was the adjacency matrix of this perfect matching, and that corresponds to vertices far apart. So the distance between them is at least log of n minus 2. So you do the calculation, the n would then simplifies, and you get log of n. So that's basically the proof. And this is an important proof because it's something similar to what we'll see a bit later, what Valentin did for distance regular graphs. Okay. So that gets me to distance regular graphs. So I assume most of you know what they are, but for maybe people who are less familiar, so you have a connected graph with diameter d. It's called distance regular if you have these constants ai, bi, ci, such that if you take any two vertices x and y, so here the distance between x and y is I, then I has bi neighbors that are further away from x, so there are bi neighbors here, and then it has ci neighbors that are closer to x, and the other neighbors ai are over here in this at the distance I from x. And as a consequence of the definition, this graph is going to be regular of valency k equals b0. Also ai plus bi plus ci is going to be k, because every vertex has k neighbors. C1 is here. C1 is going to give you 1, and here BD is going to be 0 because the graph has, not that I plus 1, but that, if this is gamma d, if you're going out, there's nowhere to go because diameter is d. Okay. Now, the same, this condition that is stated combinatorially can be rephrased in terms of the adjacency, the distance matrices of the graph. So AI is the distance I matrix of gamma, meaning that AI of xy is 1 if and only if the distance between the graph, the vertices x and y, is I in the graph. There's another question. I guess everything is, yeah, it's probably possible, but I don't know much about it. Yeah. So with the adjacency matrix, A1 is the adjacency matrix, A0 is the identity, A1 is the adjacency matrix, and then you have all these matrices all up to AD. Okay. And now from that equation, you can prove that each of these matrices, they are actually AI is actually a polynomial in the adjacency matrix in A1, and these polynomials, they're this family of orthogonal polynomials associated with the graph. You have that V0 is 1, V1 of x is x, and then you have this recurrence relation, which looks very similar to what I wrote earlier. And so basically, each of these VI has degree I. Okay, it's a polynomial of degree I. Okay, so you have this distance regular graph, you have these parameters, then you have distance matrices associated with it, and you have these polynomials representing these distance matrices. And from there, this is, needs a proof, but just believe me, you have the adjacency matrix of gamma, if you have diameter d, is going to have d plus 1 eigenvalues, and the eigenvalues, I list them as theta 0, theta 1, theta d. They are the roots of some polynomial of degree d plus 1, but also they are the eigenvalues of this quotient matrix. I guess in BCN is denoted by L, which is the quotient matrix, is the partition from distance partition from a vertex, which is equitable. It's an equitable partition, and it has this quotient matrix. So it's this kind of three-diagonal matrix, and this the eigenvalues of the big graph, the distinct eigenvalues, d plus one of them, they're going to be all the eigenvalues of this matrix. Okay. All right. So now let's come to the work of Valentin. So in 2008, he has a paper in JCTB in which he studies the least distortion of distance regular graphs, and he proves several very interesting results. So the first one is that if you have a distance regular graph, then you can always find an optimal embedding that is faithful. So he called, this is his name. So faithful means that the distance between the images of two vertices x and y only depends on the distance between x and y in the graph. So if you have two pairs of vertices, the xy, and x prime, y prime, with the distance between them the same, then in this embedding, their images also are going to be at the same distance. And this is a short proof. If you basically, he takes an embedding row with some distortion d, and from this embedding you have a gram matrix Q, which is again the dot product of the vectors rho x, and then you project he projects Q on the Bose-Mesnel algebra of the distance regular graph, which is the algebra generated by the adjacency by the distance matrices A0, A1, and AD. Now the projection, this adjacency, this algebra has two bases, the A's and the E's, which are these primitive idempotents that appeared in Chris Gotzel's talk, for example. And you can write this projection in terms of either one of them. And this first expression tells you that this Q bar is going to be positive semi-definite. And then he uses a second expression to prove that this is going to be a graph matrix of a faithful embedding, because you see here it only depends on the distance matrices. So that simplifies things, because remember that when we had this complicated expression with the numerator and denominator, at the denominator we always look for adjacent vertices x and y. And what this is saying, for distance regular graphs, at the numerator, you're just looking for one of the distances from 1 to d to put there, because you're always going to have a faithful embedding. So using that, Valentin proves this lower bound on the least distortion of a distance regular graph. And so what do we have here? We have the distance regular graph gamma, the diameter d, the d plus 1 distinct eigenvalues. K is the theta 0, is the largest eigenvalue. And the VD, these are the polynomials that I mentioned earlier, that the D adjacency matrix is the polynomial VD of A. And so the proof that he gives, if you look at it, it's quite similar in spirit to the linear Magen proof. You take Q as a linear combination. This matrix was the same before, Ki minus adjacency matrix. But now you take some multiple of the D distance matrix minus KD. KD is the valency of the distance D graph. And you have to pick alpha such that two conditions are satisfied. Well, I mean, actually one, you need Q to be positive semi-definite, because you've chosen Q as a linear combination of Ki minus A and AD minus KDI. He gets Q times 1 equals 0 immediately for free. So the alpha is chosen such that the matrix is positive semi-definite. And actually you can choose several alphas, but you also, at the same time, when you compute this expression here, since this is a lower bound for C of G square, you want this to be as large as possible. So this happens kind of, yeah, you may think strangely, for the minimum of this expression. Okay. So again, the calculations are, when you see it first time, it looks, of course, it may look quite complicated and technical. But again, remember that at the bottom, by the observation earlier, you sum up over all x and y that are adjacent. So here, the summation, this distance is going to be 1, and you just put in minus q of xy for all the adjacent vertices. And on the top, that's where this d squared comes from, because you're squaring the distance between x and y, and the only positive entries in this matrix, which are off diagonal, are going to be in over here. So that's how the d square appears there. Okay. So he proved this bound, and he showed that it's tight for all Hamming graphs. So Hamming graph HQN, and it's equal square root of n. Johnson graphs, JVK, I'll explain in a second, and strongly regular graphs. So he proved that this lower bound actually gives you the exact this distortion. And so here's a quick explanation of how does it happen for Hamming graphs. The Hamming graph HQN, the vertices are the words of length n over an alphabet q of size q, adjacent if the Hamming distance between them is 1. And he actually uses the eigenvalues of the Hamming graphs, which are given by these Krautchuk polynomials. And so here, this thing requires a proof that this lower bound is actually attained for j equals 1. He does that. And calculating things, you get that the lower bound is this one. And then you can actually find an embedding that actually gives you distortion of square root of n. And so you take this E of A, which is a vector in RQ, which is like again, Q is my alphabet. So this is my alphabet. And then if I have A1, AN in Qn a vertex, then I embedded in some constant here and a vector in this space of dimension NQ, where you have kind of the characteristic vector of each letter put into this position. And you can do this calculation that the distortion is going to be square root of n. That's what I tried to write there. And again, I think I put too many things, but yeah. So again, he proves this, the lower bound, you get some value, and he matches it by an embedding. Okay. The same thing for Johnson graph. So Johnson graph, you have the vertices, which are the k subsets of a set with v elements, and they're adjacent if and only if their intersection has size k minus 1. And again, this requires a proof. The eigenvalues of these graphs come from these Eberlein polynomials, and you get this lower bound of square root of k. And for the upper bound, he embeds, again, the vertices are k subsets of a set with v elements. So he embeds each vertex as its the characteristic vector of the k subset that it corresponds to times some constant. And this again, he shows that the embedding has distortion. I guess that's a typo here. It's not square root of n. It should be square root of k. Okay. And for strongly irregular graphs, there's he uses this result that the denominator has to be attained at vertices of distance 1. And so combined with his result about faithful embedding, the denominator in that expression has to be attained at vertices of distance 2. And that's how he proves. He doesn't give per se a concrete embedding as here. Okay. So he proves these results, and then he conjectured that the lower bound above, this lower bound is tight for all distance regular graphs. So what we proved, again, my last 5 minutes, in a joint work with Himanshu Gupta, who's a PhD at the University of Delaware, and Ferdinand, is that this conjecture is not true. So you have to be a bit careful. So let me explain why it's not true, and actually how can you salvage the conjecture. So his result, like his lower bound, there's actually part of a family of lower bounds, because in his lower bound, as you remember, he took a linear combination. This matrix was in the lower bound of Valentin, and here he had this matrix, but he had it with AD minus KDI, because he assumed that the most expanded vertices are going to be the adjacent ones. So he thought that the most contracted vertices are going to be the one at distance d. And that's actually not quite the case. So if you take this, you take an R, any R between 1 and D, and you take this matrix QR, you can do the same proof as Valentin did. And clearly QR has row sum 0 and is positive semi-definite. And you get this lower bound here. And again, when R equals D, this is the same as Valentin. But you know, R could be D minus 1 and could be smaller. It could be some other value. So let me show you what happens here. So if R, bullet 1 is the lower bound that Valentin got, and bullet 2 is what you get when you take R equals D minus 1. It becomes D minus 1 square VD minus 1K, minimum of this weird complicated expression. And it turns out that there are graphs where bound 2 is going to beat bound 1. So the example, the infinite family of graphs that we found is the family of Hadamard graphs. So these are distance regular graphs of diameter 4. They can be constructed from Hadamard matrices. It's a section in first chapter of BCN. And if you do the calculation for Valentin bound, you get that expression 8 times something. So it's about 8. And if you do the calculation for the second bound, D minus 1, you get about 9. So for mu large enough, which is at least mu always has to be even. So for mu greater or equal to 34, you get a better bound than Valentin. So his bound cannot be tight. And there are actually other examples, and this was again found by numbers, by computer and so on. And they're all antipodal, and I don't know so much about them. Himanshu and Ferdinand have gone through them. And also we have the exact calculation. I'm not going to put them here, but these are also counterexample to his conjecture. So these ones show that also it's the vertices at distance D minus 1 that are the most contracted, not the vertices at distance D. Okay. Now, how can you salvage this? I have 3 minutes. So basically, you can reformulate everything that Valentin did in terms of these cosine sequences. So representation of distance regular graph is a chapter in a famous book on algebraic combinatorics. And you can find all the details there. And so for each eigenvalue, you can define this sequence of cosines. These are some of their basic properties. And these cosine sequence, they're called standard sequence in BCN. And they also correspond to their various formulation, but they're basically W0 WD is an eigenvector corresponding to theta of this quotient matrix. Is a right eigenvector corresponding to theta. And there are many properties. You have, you know exactly how many sign changes you have, how many sign changes between consecutive differences. They satisfy this recurrence relation and so on. So I'm sorry for going a bit too fast here, but essentially Valentin conjecture can be reformulated in terms of these cosine sequences as the following: that C2 of G is D squared times the minimum of this quantity, and we show that it's not true. And here's our attempt to save it. Maybe it's not the best attempt because we come up with more conjectures. So conjecture 1 is essentially saying that we believe that this least distortion is attained when you go to distance, not only to distance D, but distance D minus 1 or D. And here there's another, you see there's a max, so that's the part about max. And then there's a part about mean over all J from 1 to D. And we believe that it's going to happen at J equals 1, that minimum. And then if you break down the two conjectures, there are actually two things in there. So we have two maybe simpler conjecture 2 and conjecture 3. And again, 2 and 3 imply the conjecture 1. And we checked both of them for all the intersection arrays on Brouwer's list. Let me quickly give you one page for each of them. So I'll start with conjecture 3. Conjecture 3 is about an embedding, and essentially says that it implies that, and I think it's actually equivalent with the fact that embedding on the second eigenspace, on the eigenspace corresponding to θ1 in a distance regular graph, is actually an optimal embedding. And this is an embedding, again, the U θ1x is the row in this matrix U θ1 corresponding to the vertex x, and you scale it there just so that it's all faithful and everything. And so, yeah, conjecture 3 implies that rho is optimal and that C2 of G equals the distortion, which is also the contraction of rho, because the expansion is 1. And we check that this is true for all graphs with classical parameters, with B greater or equal to 1 and beta sufficiently large. And we also we check that it's true for Taylor graphs. So we haven't found contra examples at diameter 3. Conjecture 2, it's in some sense it's a distance conjecture. It's basically you're looking only at the at this cosine sequence associated with θ1, and you're comparing these weird quantities with each other. I mean, it's known that the sequence W0 starts at 1, and then it goes to it's going to go down for θ1. It goes to θ1 over k and so on. It goes down. But this is a bit different. You have this quadratic thing r squared. We can prove that the minimum is attained on the second half of the diameter. It's attained for an index which is at least half of the diameter. So that proves the conjecture for diameter 3 and 4, or 4. And we can prove it for classical parameters with with b greater or equal to 1. And yeah, it has that implication, but we don't know if it's true in general. Okay, so I'll stop here. I'm sorry for going over time. So thank you very much.
Yeah, let's thank the speaker. Thank you for a nice talk. Are there any questions?
I've got 3 questions.
Oh, nice.
I also have a question.
Go ahead.
Well, somebody can go first.
Go ahead, Bill.
So I'll just go backward. So the conjecture 3, have you checked this? It makes me think of the odd graphs. So I wonder if the odd graphs behave strangely here.
Actually, we have not. So I don't remember we did that. So
Because you get this twisted eigenvalue ordering that doesn't match the the Johnson. The second question is, you project valentin has this nice thing, project orthogonally onto the adjacency algebra of a distance regular graph. You get a faithful representation. But what about an arbitrary graph? It's not going to be faithful, but would the distortion go up if I project onto the adjacency algebra of a graph?
I have no idea, actually. Yeah, I don't know. So you take a
take something that you think is good, and you just move to the closest thing in the adjacency algebra. It'd be nice if that's also good.
Yeah, that's a nice question. I don't know.
Okay, I'll save my third question. I think Crystal had the other question, right?
Yeah, I'm good. I'm 2 for 2 of not knowing.
Hey, Sebi, can you go back to the previous slide? Slide 30, please. Thanks. Okay, so conjecture 1, I'm a little bit confused because on the left-hand side, there is some quantity squared. So this is supposed to be some positive, no-negative number. But then on the other side,
I mean,
you're taking the minimum of these things.
If you want, you can. This one can go in there if you want. So
yeah, it doesn't matter. But if the diameter is even or odd, I forget how it will work. Those cosines for the least eigenspace, they alternate in sign. So it looks like it should be that this fraction is negative because one of the terms should be positive and the other one should be negative. So is this
which fraction
possible?
Which fraction is negative?
Like this, for sure, omega-1 divided by omega r should be negative for certain distances, if the distance is odd.
Okay.
It's the eigenvalue index, but it's not the distance, isn't it? Okay, I'm with you. No, I'm with you. I know what you mean. Sorry.
Yeah.
No, we're with eigenvalue D. In the
Yeah,
Dth
I
one, they
understand,
all
yeah.
alternate.
Mm-hmm.
Right. And similarly, maybe you can do also something similar to establish conjecture 3, because you want to say on the next slide, because you want to say that it does attain the maximum for the theta 1 eigenspace.
Yeah.
So for the theta 1 eigenspace, the pairwise differences of consecutive cosines all have the same sign. So the first cosine, omega 0, is always 1. So the
Yes.
denominator of this is always just omega 0 minus omega 1. And that
Yes.
top is just the sum of all the differences.
Yes.
It's like omega 0 minus omega 1 plus omega 1. So they should at least have the same sign, unlike the other cosines.
Yeah, we tried that. And we kind of went around in circles, because I think in BCN they give you different formulation for this. You have a different several formulation for this. I mean, they don't call them W. I think they're U in their formulation, and it didn't quite seem to work. But yeah, maybe we can talk more about it afterwards.
Okay.
Your standard sequence is normalized with all the values. All the values live between -1 and 1, right?
Yeah.
So both top and bottom are positive.
Yeah.
Oh, they're normalized.
Yeah.
Yeah.
Okay,
Yeah.
That's why
W0 is 1. Yeah.
They're cosines.
they're cosines. Yeah.
Right. Okay.
Sebi, did you say you'd proved the conjecture for diameter 3?
The other one. So the this one. This is not so hard, because you can do a similar trick to. So Himanshu did this, and you can do a similar trick to how they showed that the most expanded pairs are a distance 1. You can play a game like that with some distances and so on, and you can these expressions you can write them in terms of an embedding, and But we don't. This one we don't have it for just
so
for.
You're saying conjecture 3 is true for Taylor graphs, so that's double covers, antipodal double cover with the graphs.
Yeah.
What about covers with larger index?
Yeah, we didn't find any. So yeah, that's the other thing. Like we believe that this D-1 business just appears when for antipodal of covers of like Hadamard graphs and so on. But for any others, the valentin conjecture was true. This maximum was a D. So yeah, like all the other examples. Yeah, these ones. Sorry, where am I? Yeah, here. So yeah. They're all 2 covers. So.
Yeah.
But aren't these all also Q antipodal? So that last eigenspace has some special property. The Hadamard graph is Q antipodal as well.
Q antipodal just means bipartite.
Sorry, Q bipartite.
Yeah.
Yeah.
Yeah. But I mean, there are other So yeah, we thought that the only time we win is for this antipodal for sub-antipodal, but we don't win for all antipodal graphs, I think. So we don't know what's going on.
So maybe you need to be like cometric and then also Q bipartite or something.
Yeah, we tried to work with the Q polynomial stuff, but it's we couldn't figure it out. Yeah.
Are there any other questions?
So this is very far-fetched, but this reminds me of a talk in data science and representing finite metric spaces in smaller dimensions. So is it possible to have an embedding on row which works for a reasonable collection of graphs, not just for one graph? Can you find a single row that works for a reasonable fraction of graphs on n vertices? I mean, and not of course optimal, but let's say within some factor of optimal distortion.
Yeah, I mean, I believe in the second eigenvalue, like for the, at least for the regular graphs, you know what I mean? I think, I mean, if I were to guess, if you go to the other graphs, maybe you go to the algebraic connectivity eigenvector or something like that. I don't know if how would that work, but for like, basically when, you know, we're looking at what Valentin did, and we look at the embedding that he used, and, you know, you read the, you know, Gotzel algebraic combinatorics and so on, and it's the same this representation of the K subsets by their characteristic vectors and so on. So that's why I ask Himanshu, let's look at the embedding on a certain eigenspace, and I believe it's the one corresponding to the second eigenvalue that's going to give you optimal.
Yeah, the question seems vaguely reminiscent of the Rip property of, it seems a bit Rippish, but not in any precise way.
So what happened to the Grassmann graphs?
It's correct. The Valentin is true.
Yeah, okay.
Yeah, Valentin is true. So these are the ones that I listed are the only ones that counterexample that we saw.
Yeah.
And so again,
and they all have low diameter. Did you check the pathological graph with huge diameter?
No, so they have diameter 4. I think there were 5, 6, and 7. So that's all. Yeah.
Okay.
Oh yeah.
Did you check the Biggs-Smith graph or whatever its name is that has irrational eigenvalues?
Yeah, so I think we checked, like I said, all the ones on the Brouwer list. So the intersection array, yeah, so the intersection arrays on Brouwer's list. And yeah, our conjecture is true, and the only one that failed Valentin conjecture are these ones.
Now, there are other antipodal covers. The Hadamard graphs are double covers of complete biproduct graphs.
Yeah.
With index 2. So there are covers with larger index. What happens with them?
From what we haven't gotten an example from there, but I don't know off the top of my head what's the distortion and all that stuff. I have to check. Yeah. I have a question for Crystal. What chapter is a representation of distance regular graph in algebraic combinatorics? The number.
2.
No.
1.
No.
5.
No.
6. Give me a sec.
She's got an algorithm, but it's fairly slow.
1, 2, 3, 4.
You're not going to get to that quickly then.
No, it's in several different ones, right? So it's in
No.
No. It's just
13. It's 13.
Very good.
Oh, yeah. That was going to be my guess.
Yeah. Yeah.
But if there are no more formal questions, let's just thank the speaker again.
Thank you, Maria. Thank you, everyone.
Thanks, Maria.